fourth part of MOSFET lecture, we talked of how we can how you derive the current through the transistor ID. Okay, ID given the drain voltage VDS and the gate voltage VGS. Okay, so to turn on the transistor, you recall that VGS should be greater than the should be greater than the threshold voltage. So the transistor is on. Okay, if VGS is less than the threshold voltage VDN, the transistor is in cutoff. Okay, so you don't want that. The transistor is in cutoff means that your ID is very small. Okay, then there could be a leakage current, but that's not significant. So this is if the transistor is off. Okay, now if you have satisfied this condition, you have the gate voltage greater than the threshold voltage. Well, there are two ways to find the current that flows through the transistor from drain to source. Okay, to see that how you can evaluate that analytically. One is you if you have the graphs. Okay, one way is to evaluate ID, the parameter current flowing from drain to source, given whatever the drain source voltage is, you can find the current. Okay, so let's say if VDS your VDS is in the saturation. Okay, so that VDS applied is greater than VDS sat. Okay, you're somewhere in the saturation region. Well, you can look at the curve that increasing VDS thereafter at that point does not increases the current ID. Okay, but this is actually beyond this point where we have the saturation. ID is not increasing. Okay, these are the points. Now, if it is the other way around, VDS is less than VDS sat, then you can use this relationship. Okay, this is for the non-saturation or the linear or triode region, and analytically you can find what the drain to source current is in the transistor, given you have this parameter Kn. Okay, this Kn is the transconductance parameter, which is expressed in terms of the electrical parameter and the geometrical parameters of MOSFET. Okay, so for the given VGS, you should have the threshold voltage. Okay, which is determined from the given fabrication parameters of the transistor. And for the given drain source voltage, you can find what the current is. Okay, that can be done either graphically or through analytically using the given current and voltage relationships. So okay, so in the saturation, you can use this relationship for the given VGS and VDN, and you can find the drain source current from here. You see, the point is, if you're looking at this scenario graphically, then VGS is for each curve there is an associated VGS. Okay, so you have to know VGS as well. This must be known. So VGS must be known. So this should be known. So for the given VGS, you select that curve, and then for the given VDS, just find that ID what it is if you are in the saturation region. Okay, if you are in a non-sat region like this, okay, then you can find the drain current, which will be lower than what you can have in the saturation. Okay, but if you have the if Kn is known, if you have Kn, okay, which is determined from the geometrical parameters, width and length of the transistor, and you know what is the capacitance of oxide, that is per unit area, given by the permittivity and the thickness of the oxide, and the mobility of course, the mobility of electrons, mobility of the electrons if it is an NMOS MOSFET, you can find Kn. Okay, then you can plug this Kn in this expression, and you can find what ID is. And you see that the thing is, if your ID can be increased, or I must say it is set by the given geometrical parameters W and L. Okay, you cannot do anything about this transconductance parameter. because the geometrical parameters, electrical parameters are already set during the fabrication of MOSFET. Okay, so it's the designer's choice. If he has to, if he chooses to increase the ratio of W to L or increase the transistor width, well, you can have more, drain to source current. Okay, but again, it depends on the geometry of the MOSFET. Now, let's have a look at the example that illustrates this idea. So, you consider an N-channel enhancement mode MOSFET with the following parameters. The threshold voltage is given as 0.4 volts. The width and the length are 0.20 and 0.8 micrometers. Mobility is given in centimeters squared divided by volt seconds. Thickness of the oxide is 200 angstroms, and epsilon oxide, silicon dioxide is 3.9, 8.85, 10 to the power minus 14 farads per centimeter. So what you need is to determine the current that flows through the transistor when it is biased in the saturation region. Okay, so there are two parts. VGS for one is VGS 0.8 volts, and the other is 1.6 volts. So what it says is that you have two VGS. Okay, so you will have two family of curves like this. One would be 1.6, the other is 0.8. Okay, so you select those two curves. You have VGS, and then it is giving you the threshold voltage 0.4 volts. Okay, and in both cases the transistor is on. So we are talking of the transistor. The transistor is biased in the saturation region. Okay, the transistor is already biased in the saturation region, which means VDS was already greater than VDS sat. Okay, so the applied VDS is greater than VDS sat over here. That's how we are we have reached the saturation region. So the solution to the current can be found two ways. One is you have the graph and you have the values, and you can look up for the given VDS, for the given, if you have the given VDS value, you can just look it up from the graph. The other is to use analytical expression. So for example, for this saturation region, okay, since we have the geometrical and electrical parameters, we can find what Kn is. That's the first thing. And for each given VGS, we have the transistor threshold voltage that is constant. So all we need to do is you use this expression in the saturation to find what is the current that flows to the transistor. Okay, so let's find K of n. K of n, remember, is given in terms of the geometrical and electrical parameters. So let's try to find this out first. So okay, the width of the transistor is 20 micrometers. You see that these are like practical values, which says that MOSFETs are very small and they can be used to make very large scale integrated circuits and digital circuits. So substituting these values of width and length, then you have the mobility. Okay, if you have to convert this is in centimeter square, you can make it in meter squares. Okay, and then you are left with the capacitance of the oxide. Capacitance of the oxide is the ratio of the permittivity, electric permittivity to the thickness, and so this is what you get in farads, millifarads. This is millifarads per meter squares. So if you plug this over here, you can find K of n as 1.41 milliamps per volt squares. All right, and then you can use the equation of you have K of n. Okay, so you can use the analytical expression for the current and the voltage. So we have two values of VGS. Okay, since we don't have VDS, we cannot go for a graphical solution over here. So from the VGS and VDN is 0.4 volts, which is given over here. Okay, this is your VDN. So in both cases, just plug the VGS values. Okay, the VGS is 0.8 volts for part A, and then this is 1.6 volt. Kn is fixed. This is your Kn, and this gives you the current in both cases. Okay, so once you have this Kn, you have VGS 0.8 and 1.6. You get for 0.8 volts, since your gate voltage is not creating that much of an electric field, so you don't have much of the charge density in the channel. So the current flow that is expected is small. And then if you, for example, if you double you make the gate voltage as twice of what you had before in part A, 1.6 volts, the current doesn't become twice. Okay, this shows that the device is inherently non-linear because the VI characteristics are non-linear. So MOSFETs are non-linear electrical device. Uh, you can still increase the current by increasing the width of the transistor, which is included in the parameter K of n. So there's the width. Okay, you can still increase that, but this is fixed. Once the MOSFET is fabricated, you have the dimensions of the gate and the transistor. Everything is fixed. Mobility is fixed. Capacitance of the oxide is fixed. So for the given K, there's not much you can do. But yes, you can vary the current to applying more VGS. Okay. Uh, so as you see, as you have more VGS, the channel width increases, space charge density in the channel width increases, and this results in more current, which is shown over here. Okay, that's all.